In this video, I'm going to talk about all of the vertex form stuff that we've done this week, as well as some older topics from before the midterm like quadratic regression, quadratic linear systems, and some word problems with quadratics. So to start off, we need the general form for vertex form of a parabola, and that's y equals a times x minus h squared plus k, where h comma k represent the x and y coordinates of the vertex, hence the name of the form. So we need to ask ourselves, what do these values actually do to our parabola as we change them? So for that a value, what I have it set up right now is I have an a value of 1. And as I increase the a value or decrease the a value, notice what happens. It gets, as I increase a to a larger number, the graph gets narrower, but as I decrease a to a number between 0 and 1, it actually gets a little bit wider and wider and wider until it flips and reflects over the x-axis and does the same thing on the other side. So for the a value, we call that a vertical stretch or vertical shrink. So the a value vertically stretches or shrinks the graph. For the h value, well, we already know that represents the h coordinate of the vertex. But if we think about how that affects the placement of the parabola on the plane, if we increase h, it moves to the right, and as we decrease h to make it a negative number, it moves to the left. Notice though that the formula already has minus h in there, so when you plug in a negative 3.3 for h, that's going to look like a positive value. So when you see positive values in the formula, that means move to the left, and when you're subtracting just regular positive numbers, x minus 6.7, you move to the right. So this would be a horizontal shift, so either left or right. And if the k value is changing the y value of the vertex, that's just changing the vertical placement of the parabola. So it's either moving up or down. So that's a vertical shift. So if we see something like number 5, where it's asking, you have a quadratic that looks like f of x, and we don't know what f of x is, it doesn't matter what it is, it's just a quadratic, and you have another function, g of x, defined to be f of x plus 2, and you need to ask yourself, what kind of transformation is this? Well, if you're looking at that vertex form formula from before, this is a plus 2 in the parentheses, so it's affecting the x values. So since it's changing the x values, the x-axis runs left to right. So I know this is going to be a horizontal change. And when I'm adding 2 to x, that's going to be a shift of 2 units left. So when the change is in the parentheses and it's changing the x, it's the opposite of what you would think. And if you're not sure, take a look at the graph of y equals x squared compared to y equals x plus 2 squared, and you'll see that the second one is moved 2 units left. For number 6, a very similar problem, but notice that the change is now outside the parentheses. So it's like we take all of our f of x values and we're subtracting 4 from them. Remember that when we're graphing, these f of x values also represent y values. So it's like I'm taking 4 away from all my y values, or shifting down 4 units. So it's a vertical change now because it's outside the parentheses. It's not affecting the x values anymore. It's affecting the y values. Number 7. The equation f of x equals x squared plus 2x minus 3 represents a quadratic in standard form. Write this quadratic in vertex form. Well, if you think about the vertex form from the last page, we're going to need an a value, an h value, and a k value. So that a value is always the number out in front, that leading coefficient. In this case, our a value equals 1. And we need to think about how to get our h values and our k values. For this, we need to be a little creative if we're doing it algebraically. Of course, you could always just plug this into the calculator and look at the table to see where the graph turns around. But if you want to do it algebraically, you would use the axis of symmetry formula, because the axis of symmetry represents the same x value that your vertex has. So I already labeled an a, b, and a c in my standard form of a quadratic up here, so I'm just going to substitute those values in. My b value is 2, and my a value is 1. So negative 2 divided by 2 times 1 is just negative 1. So I know the x-coordinate of my vertex, or the h value in my equation, is going to be negative 1. So here's the scenario. We've got the x-coordinate of the vertex, but we're still searching for that y-coordinate. Well, we have the function already, so if we know what an x value is and we're looking for a corresponding y value, we can just substitute that value in. So we're going to find what f of negative 1 is, and substitute in a negative 1 everywhere we see an x in the equation. And when we do that, negative 1 squared is positive 1, 2 times negative 1 is minus 2, and minus 3. So we get 1 minus 2 minus 3, or negative 4 as our k value. So when we plug into the vertex form, y equals, my a value is 1, so I'm not even going to write it, x minus negative 1 squared plus negative 4. So that's how the formula would tell me to substitute it in, but there's some stuff we could do to clean it up there. Y equals x minus a negative 1 is just plus 1 squared and minus 4. So my final answer would look just like this. So for something like part B, where it asks us to do the same thing, you would follow the same exact process, where you find the axis of symmetry, and then use that to substitute in to find the y value of your vertex, or that k that you're looking for in the formula. Number 8. Given f of x equals x squared, state the quadratic equation g of x in vertex form that will translate f of x 5 units up, 4 units right, and reflect it over the x-axis, and has a vertical stretch by a factor of 3. Okay, so I know if they're talking about a vertical stretch, that's going to be the a value. And if I'm reflecting it, that just means that a is going to be negative. Any sort of horizontal shift is the h value, because that's affecting the x. And any sort of vertical shift is affecting the k value. So if I think about the formula for vertex form again, all I need are those 3 pieces there. Well, it tells me the vertical stretch has to be a factor of 3, so I know a equals 3, but they tell me it has to reflect over the x-axis, so a is actually negative 3. And I want to move 4 units to the right, so my h value is going to be 4, because when I subtract a number from x in the parentheses, that's going to move the graph right. And to move 5 units up, I add 5 to the whole thing. And that would take all of these f of x values and scoot them up 5 units. So this is what the final equation would look like. Number 9. Given the table below, explain how you know this table represents a quadratic function. Well, in order to look at a table and see a quadratic function, you need to look at the rates of change between each of the points. So I'm going to do this just by subtracting the y values. So to get from 36 to 25, 25 minus 36 is negative 11. I went down 11 to get there. And then to get from 25 to 16, I went down 9. And then to get from 16 to 9, I went down 7. Then I went down 5. Then I went down 3. And then I went down 1. So this is our rate of change between each of the sets of points. So if this rate of change was constant, this would represent a line. In order to see if it represents a quadratic function, we just look at the rate of the rate. So here I have the first differences, this -11, -9, and I just look at the distance between those two numbers. To get from -11 to -9, I would add 2. And then to get from -9 to -7, I would add 2. Same deal for -7 to -5, -5 to -3, and -3 to -1. So in this case, this second difference here, or the rate of change of the rate of change, is constant. That means that a quadratic function would best be suited for this data. So if you're asked to explain how you know, you could say the rate of the rate is constant. So since the rate of the rate of change is constant, we know this has to be a quadratic function. And now they asked us to write the equation of the quadratic function in standard form. So recall that standard form is ax squared plus bx plus c. So I need some sort of x squared term and then some other stuff after that. In order to do this, we need to go to our calculator. Okay, so in order to input this data into our calculator, we go to Stat, and we go to Edit. Then we put all of our x values into L1, and all of our y values into L2. Once you have all your x and y values in, I just like to double check that I have everything in there and it matches my table exactly. So in this case it does. So I'm going to go back to Stat now. I'm going to arrow over to Calc and go all the way down to number 5 where it says Quadratic Regression. So it's going to ask us for the x list, make sure that's L1. It's going to ask us for the y list, make sure that's L2. Hit enter a few more times to where you get to calculate, and now it gives you this equation. It shows it in standard form, where the a value is going to be 1, the b value is -6, and the c value is 9. So it already took that data and figured out what the a value is going to be, what the b value is going to be, and the c value. And that would be the equation of this table right here. And if you're asked to explain how you arrived at your equation, you would just describe what you did in the calculator. So you would say that you put your x values into L1 and your y values into L2. Then you went to Stat, Calc, Quadratic Regression, and hit enter. That's all you need to say for this if you did it all in the calculator. So for number 10, they ask us to graph g of x equals x minus 3 quantity squared plus 5. So I already took the liberty of plugging it into y equals, going to the table, and looking for some nice symmetry. So I'd be able to single out my vertex right in the middle there, that 3, 5. But if you know a little bit about vertex form of a parabola, you don't even need to do all that work to find the vertex, because it's just this h value, comma this k value, 3, 5. So the first question it asks us is to compare it to f of x equals x squared. So that parabola is centered at the origin with a vertex of 0, 0, and it opens upward as well. So that's not a great estimation of it, but it gets the point across. So I can look at g of x and figure it out, or I can look at the graph and figure it out. So if you want to, you could type in x squared into y1, type in this function into y2, and just see what changed. But if you remember what h and k do in terms of transformations, this question's a lot easier. Because when you subtract a number to x, that moves it right. So you know you shift right 3 units. And when you're adding a number on the outside, that k value, that represents the vertical shift. So it also goes up 5 units. I didn't even need to type anything in there. I'm done in 2 seconds. So it's in your best interest to get into the habit of recognizing those transformation rules for quadratics. over what domain is the function increasing? So I'll get my f of x out of there. And for a function that's increasing, we're looking at when it's doing this, going up. So as I'm reading my parabola from left to right, it looks like it goes down on this side and then goes up on this side. The turning point is that 3, 5. So it looks like all of the x values after that 3 right there have the function increasing. Because remember, domain represents a set of x values. So in this instance, I could say that the domain that works here is x is greater than 3, or if you want to write it in interval notation, -3, infinity, both in parentheses. Notice that I don't have x is greater than or equal to 3, because at 3, the graph is neither decreasing nor increasing. That's the very second when it's turning around, so I can't include that in the interval. Then it asks for the range of the function. Range represents the y values, or how far up and down the graph goes. So the first thing you need to ask yourself is, does the graph have a minimum or a maximum? In this case, since the graph goes down and then comes back up, this graph has a minimum. So the minimum value of y that you have here is the value you see in the vertex. So the minimum value is 5, so we're going to use that somewhere. And it looks like these arrows at the end of the parabola mean that the graph's going to continue going up forever. So y actually doesn't have any maximum value here. The only constraint is that y is greater than or equal to 5. So in this case, the range would look like y is greater than or equal to 5, or if you want to write it in interval notation, 5, infinity. Notice that the 5 has a bracket around it because it can be included in the interval because y can also be equal to 5. And if this was a downward opening parabola and it would have a max, the sign would just be flipping the other way for the inequality. Number 11. The vertex of the parabola represented by f of x is 1, -4. So I'm just going to plot that. I don't know if I need it yet, but it could be useful. Okay, so there's the vertex for f of x. Find the coordinates of the vertex of the parabola defined by g of x equals f of x minus 3. Okay, so right off the bat, I'm seeing that I'm subtracting 3 from the x value, so I know this has to be some sort of horizontal shift. Remember that when you're subtracting a number from x, that's going to be a shift to the right. So in this case, I could just take the original vertex I have and move that over 1, 2, 3 to the right to find my vertex for g of x. So that coordinate would just be 4, -4. So that's how we would show it graphically, just by moving the point over. To show it without a graph, we could see that f of x minus 3 means shift 3 units right. And in order to shift a point 3 units right, all you would have to do is, if you look at this vertex and the original vertex, all you have to do is add 3 to the x value. So you can just take 1, -4, add 3 to the x value to show that this would be your new vertex. The reason why the y value doesn't change is because there's no vertical shift here. It's only a horizontal. Number 12. Graph the quadratic linear system. So you've got a parabola there and a linear equation as well. So I've already graphed the parabola by plugging it into y equals, going to the table, looking for symmetry, and that's old news right now. And even this g of x should be old news too. If you don't remember how to graph a line, usually I think about it in slope-intercept form, where m is the slope and b is the y-intercept. So if I'm taking a look at g of x here, I know that the slope represented by m is going to be -2, And I know that the y-intercept, represented by b, is going to be positive 6. So if you want to write the slope as a fraction to make it easier to see what you're going to do here, I'm just going to write it as negative 2 over 1. So my y-intercept is 6, so I'm going to start at 6. And if my slope is negative 2 over 1, remember that represents the change in y over the change in x. So I'm going to go down 2, right 1. Down 2, right 1. Down 2, right 1. Down 2, right 1. And I'll get a couple points above it as well. Up to left 1, up to left 1. And you can connect them with a straight edge. Now I don't have a straight edge right now, so I'm going to do my best, but you get the idea. So this is what this system of equations looks like. It's a parabola intersected by a line at 2 points, right here and right here. So let's see what the question asks from us. The question asks, state the solutions to the system. The solutions to the system are the points that both of the graphs have in common. So in this case, it looks like negative 1, 8 was that first point that they have in common, and the other point that they have in common right there is 3, 0. For part B, it asks what values of x does f of x equal g of x. That's actually asking the same exact question. It's saying what values of x would you have to plug into both of these functions to get the same output. That's equivalent to looking at where the graphs intersect. Well, since they intersect at negative 1, 8, x equals negative 1 would be one of the values, and x equals 3 would be the other value. You can do this graphically by going to your calculator, getting a table, plotting the line, doing it on graph paper, or if you're a little bit clever, you could do it in your calculator as well. Okay, so I've graphed these two functions in my calculator, one of them in y1, the other one in y2, and I'm going to figure out how to do this whole process in my calculator. So the first thing you want to do is hit the second button, and then hit the trace button, and that'll bring you to this calculate screen. And we're looking for the solutions for this system, so we're looking for the points where they intersect. So you're going to go down to 5. Then it's going to ask you in the bottom corner, first curve. So it's got me locked on the parabola because I have that in y1. I'm going to arrow over to where I think the intersection point is and hit enter. Then it's going to ask me for the second curve. I'm going to hit enter again. And then it's going to try to guess. So I hit enter one more time. And look at the point it gave me there. X equals negative 1, y equals 8. That's that first point that we already solved for down there. In order to find the second point, you would just do the same process. Hit second, calc, go down to intersect or hit number 5, and just arrow over to the other point. Oops. So I'm still going to arrow over to the point. I'm along my parabola here. And when you get close to the intersection point, you should notice the x value is approaching 3 as it should be. I hit enter one more time, and then it's going to guess, and I hit enter. And then it gives me that second point of intersection. So keep that in mind that if you're not sure if you solved this system correctly, you can always go to your calculator and do that just to check to make sure you found the right points of intersection. Number 13. The height in feet of a rocket launch can be modeled by the equation h of t equals negative t squared, negative 16t squared plus 96t. And then it gives me a graph, and I need to plot the points and get a nice scale on the x and y axis. So notice that the x-axis is in time, so this input, this t value, represents the time that the rocket was launched, so 1, 2, 3, 4, all the way up to 6 seconds. And the h of t represents the height. So it's like all of the points that I have in this graph are going to be some time, comma, height. That's what all these points are going to represent. Keep that in mind. Now, the graphing part is nothing new. We just go to the calculator, go to the table, and look for symmetry. 0, 80, 128, 144, 128, 80, 0. The only tricky part about this one, graphing, is figuring out what scale to put on the x-axis and the y-axis. Here I did this by trial and error, but I noticed that there were 25 spaces on the bottom, and I needed to break it up into 6 equal parts, so I just made each of them 4 spaces long. And it doesn't have to look exactly like this. You could choose a different scale if you want. Just make sure it fills up most of the graph that they give you. And then on the y-axis, I went by tens here. But I only marked each 20th, just to make it a little bit cleaner to look at. Okay, so I got part A down, I graphed the function. Then it asks, how long does it take the rocket to reach its maximum height? So this graph represents the path of the rocket. It goes up, it goes up, it goes up, it goes up, and then it hits this maximum height right here at 3 seconds, and then it starts to come back down. So that vertex of the parabola, that 3, 144, that's the point we're going to be honing in on here. So if they're asking for how long, I know I'm looking for some sort of time. But if I already know the x values represent the time here, then I know that at 3 seconds, the graph reached its max height. So it takes 3 seconds. Then if they ask me what the maximum height of the rocket is, well, if at 3 seconds it reaches its max height, I know that y value represents the height, so my maximum height is 144 feet. Make sure to use the units they give you in the problem. That's a good way to lose a point on a test if you forget those.